Hi everyone. Already we have completed the two chapters. The first one is the chemical kinetics and the second one is the investigation of the molecular structure. From this lecture, we are going to begin the next chapter, that is the phase rule. So here let us consider the syllabus of the phase rule. So the definitions: Gibbs phase rule, one component system at moderate pressure only. So here the one component systems such as sulfur and the water systems, then two component system for silver, lead and zinc, cadmium. So here friends, this is the syllabus of the phase rule. So here in today's lecture, we are going to discuss some basic concept of the phase rule or the basic definition of the phase rule. So here system in which constituents are present in two or more phases or two or more states are called as the heterogeneous system, and the equilibrium existing between these phases of heterogeneous system are called as the polyphase or the heterogeneous equilibrium. So here in the phase rule, we are going to consider the heterogeneous equilibria. The study of the heterogeneous equilibria can be made with the help of the law of mass action, Nernst partition law, Clapeyron equation and the phase rule. So here friend, just to study the heterogeneous equilibria. So here heterogeneous equilibria can be studied with the help of the law of mass action, Nernst partition law, Clapeyron equation and the phase rule. In this chapter, we are going to discuss the phase rule. So here the phase rule is an important generalization dealing with the heterogeneous equilibria. And here the phase rule predicts qualitatively the effect of temperature, pressure and concentration and on polyphase equilibria. So phase rule was discovered by the J.W. Gibbs. J.W. Gibbs, he is the American physicist. In 1975, he discovered the phase rule. So here the phase rule, it is called as the Gibbs phase rule. So here let us consider the basic concept or the basic definition which are very useful in the chapter phase rule. First of all, let us discuss the phase rule. So Gibbs phase rule states that the heterogeneous system in equilibrium, the sum of number of phases and number of degrees of freedoms is equal to the number of component plus 2. So here mathematically the phase rule, it is expressed as P plus F is equal to C plus 2. So here this is the mathematical equation for the phase rule, and in this equation what is meant by P? P is the number of phases. What is meant by F? F is the number of degrees of freedom, or F is the degrees of freedom. What is the C? C is the number of components. And here this 2, it stands for additional variable of temperature and pressure besides concentration variable. So here these are the various terms which involve in the mathematical expression of the phase rule, and in this lecture we are going to consider, or we are going to define, that is the P phase, then F degree of freedom, C number of component as well as the system. So meaning of terms used in the phase rule. So the first term is the system. So here system, it is denoted by symbol S. A system in connection with the phase rule, it is defined as a substance or a mixture of substances which is isolated in some way from other substances. So we want to study the effect of pressure, temperature and the characteristics properties of the other constituent of a system on the physical state of the material present. So system, it is denoted by symbol S. So this is the first terms in the phase rule. Then the second and the very important term, that is a phase. So phase, it is denoted by symbol P. So what is the definition of the phase, or what is my phase? So here the phase is defined as homogeneous, physically distinct and mechanically separable part of the system, and is in dynamic equilibrium with the other parts or phases through the transition of the substances. So it is called as the phase. So here the phase is separated from the other parts of the heterogeneous system by visible dividing surfaces or boundaries called as the interfaces. So here if the system consisting only one phase, then such a system it is called as the homogeneous system. So here homo means same, geneous means phases. So here the homogeneous system. A system consisting of more than one phases is said to be heterogeneous system, or it is a polyphase. So here in order to have clear cut idea of the term phase, consider some examples. So the first example is the pure substances. So friends, when we consider the pure substances such as the solid, pure liquid or pure gas, they made up of one chemical species only, is considered as a one phase. So here when we consider the pure solid, then here in case of the pure solid, the value of the phase or P is equal to 1. In case of the pure liquid, again P is equal to 1. In case of the pure gas, again P is equal to 1. So this is the first example. Second example, mixture of the gases. So all gases mix freely to form the homogeneous mixture. Therefore, mixture of gases such as the mixture of hydrogen and nitrogen is one phase system, or hydrogen plus nitrogen plus carbon dioxide, again it is a one phase system. So here mixture of gases, in case of the mixture of gases, P is equal to 1. Then here the miscible liquids. Two completely miscible liquids yield uniform solution. Thus solution of the water and ethanol is one phase system. If the two liquids they are miscible with each other, then here in such miscible liquid P is equal to 1. So in case of the water and ethanol, they are miscible liquids. So here P is equal to 1. A mixture of the two non-miscible liquids or standing form the two separate layer, hence mixture of chloroform and water constituent two phase system. So here when we consider mixture of the chloroform and the water, in this case P is equal to 2. So here the chloroform and water, these two are the immiscible liquid. So here the P is equal to 2. Then here an aqueous solution of the solid substance such as the potassium chloride or urea. When the potassium chloride or when the urea dissolve in the water, it dissolve in the water and here uniform throughout. Therefore, it is a one phase system. So here when we consider the solution of the potassium chloride or the solution of the urea in the water, it is a one phase system. However, the saturated solution of the potassium nitrate or potassium chloride in contact with the excess solid potassium nitrate or potassium chloride, it is a two phase system. So this is the third example of the phase. Then here next one is the mixture of solids. So such a mixtures are heterogeneous and have the phases equal to the number of different solids. So example here when we consider the ordinary sulfur. So ordinary sulfur, it is a mixture of the two allotropes, that is a rhombic and monoclinic sulfur. So here the rhombic sulfur and the monoclinic sulfur are the allotropes of the sulfur. So these allotropes have same chemical composition. So here again it is a denoted by symbol S, but different in physical properties. Hence allotropic mixture has phases equal to the number of allotropes. So in case of the sulfur, there are two allotropes, that is a rhombic sulfur as well as the monoclinic sulfur. So here in case of the sulfur system, there are two phases, that is a phase 1 is the rhombic sulfur and phase 2 is the monoclinic sulfur. So these are the some example just to understand the concept of the phase. Then the second terms, which is very important in case of the phase rule, that is a component and it is denoted by symbol C. So here every substance that can be separated from the system and exist outside of it is called as the constituent substance or the constituent of the system. So here once again consider example in aqueous solution of the sodium chloride. The constituents are the water and the sodium chloride. the ions Na plus and the Cl minus cannot be included among the constituents. So, there are two constituents, that is the H2O and NaCl. The constituents whose concentration determine the composition of the phase of a given equilibrium system are called independent constituent or the component of the system. So, here any constituent may be selected as a component. So, let us define what is meant by component. A minimum number of independent variable constituent by means of which composition of the each phase can be expressed either directly or in the form of the chemical equation is defined as components. So, once again let us consider the definition of the component. The minimum number of independent variable constituent by means of which composition of each phase can be expressed either directly or in the form of the chemical equation is defined component. So, let us consider some example just to understand the term component. So, the first example, water system. So, here the water system consists of the three phases, that is ice, water and water vapors. So, here it is the one component system. So, here friend, water, when we consider the water system, so one component system, that means here C is equal to 1. So, as each phase is essentially a different physical form. So, this is a solid, this is a liquid and this is the gases. So, here the each phase is essentially different physical form of the same chemical compound, that is water, and represented by the H2O. So, here the ice, again it is a H2O, water its chemical composition is H2O, vapor again it is a H2O. So, here the C is equal to 1. So, water system, it is a one component system. Second example is the sulfur system. Sulfur system has the four phases, that is the rhombic sulfur, monoclinic sulfur, liquid sulfur and the vapor sulfur. So, here the composition of all these phases can be expressed by the one chemical individual, that is the sulfur. So, here hence the sulfur system is the one component system. So, here the chemical composition of the rhombic sulfur, it is a S, then monoclinic sulfur again it is a S, then liquid sulfur as well as the vapor sulfur again it is a S. So, here the sulfur system, it is one component system. Then the third example is the mixture of gases. A mixture of gases, say mixture of the oxygen and the nitrogen constituent one phase only. So, just we have discussed here the mixture of gases, it is a P is equal to 1, that is a one phase only, or it is a one phase system. Its composition can be expressed by the two chemical substances, that is the oxygen and the nitrogen. Hence, the mixture of the oxygen nitrogen has the two component. So, here the mixture of oxygen nitrogen, it has the two components. So, here C is equal to 2. Then here next example is the potassium chloride solution. A solution of the potassium chloride in water is one phase system, because potassium chloride is completely dissolved in the water. So, it is a one phase system. Its composition can be expressed in terms of the two chemical individual, that is the potassium chloride and the water. So, here the C is equal to 2. When we consider the saturated solution of the potassium chloride in conduct with the excess of, or it contain the excess of the solid potassium chloride has two phases, namely the aqueous solution as well as the solid potassium chloride. So, the composition of the both the phases can be expressed in terms of the two chemical individual, that is the KCl and the potassium chloride that and the water. So, here saturated solution of the potassium chloride is the two component system, here the C is equal to 2. Then the next example, that is the chemical composition or chemical reaction. So, let us consider the example of the dissociation of calcium carbonate. So, here the when there is a dissociation of the calcium carbonate solid, we get the calcium oxides in the solid state as well as the carbon dioxide in the gaseous state. So, here in this reaction there are three phases. So, here the first phase, that is the calcium carbonate solid phase, calcium oxide solid phase and carbon dioxide the gas phase. So, here the two solid phases and here the one gas phase. These three phases, they are in equilibrium in a single component cannot be used to express, a single component cannot be used to express the composition of all these three phases. But taking any two component, composition of any phase can be expressed. So, here there are three phases, two solid phases and the one gas phase. So, by taking any two component, the composition of the third phase can be expressed. So, here the first the first case, when calcium carbonate and calcium oxide are the two component, then we can write here in the first column there is a phase, in the second column there is a component. So, here the calcium carbonate is equal to calcium carbonate plus 0 calcium oxide. Then here the calcium oxide is equal to 0 calcium oxide plus calcium 0 calcium carbonate plus calcium oxide. Then here the carbon dioxide is equal to calcium carbonate minus calcium oxide. So, this is the first case when we consider the calcium carbonate and calcium oxide. Then the second case, when we consider the calcium carbonate and carbon dioxide are the two component, then we can write the phase calcium carbonate is equal to calcium carbonate plus 0 carbon dioxide. Then when we consider the carbon dioxide, then here the 0 calcium carbon dioxide plus carbon dioxide. Then calcium carbonate is equal to calcium oxide is equal to calcium carbonate minus carbon dioxide. This is the second case. Then third case, when we consider the calcium oxide and carbon dioxide are the two component, then here we can write the phase calcium carbonate is equal to calcium oxide plus carbon dioxide. Then second one is the calcium oxide is equal to calcium oxide plus 0 carbon dioxide. Then carbon dioxide is equal to 0 calcium oxide plus carbon dioxide. So, here the if the system consists of the three phases in a state of equilibrium, in the decomposition of the calcium carbonate there are three phases in a state of equilibrium. So, here any two of the three chemical substances can be chosen to express the composition of each and every phase present in the system. So, here in general decomposition of the any carbonate is the two component system. Similarly, here the dissociation of the potassium chloride. So, dissociation of the potassium chloride, it is the two component system. So, here the decomposition of the calcium carbonate, it is also the two component system. So, these are the some example just to understand the concept of the component. So, here component, then the next and the last point is the degree of freedom. Again, the degree of freedom is also one of the important concept or one of the important term in the phase rule. So, degree of freedom, it is denoted by symbol F. So, here the degree of freedom represented by the F in the phase rule equation, and it is defined as the, what is the definition of the degree of freedom? It is defined as minimum number of independent variable. So, which are the independent variable? Temperature, pressure and concentration or the composition, which must be specified in order to define system completely. So, here this degree of freedom, it is also frequently called as the variance. So, once again let us consider the definition of the degree of freedom. So, degree of freedom is defined as minimum number of independent variables such as the temperature, pressure and concentration or composition, which must be specified in order to define the system completely. So, here the system having one degree of freedom. So, here F is equal to 1, then such a system, it is called the univariant or the monovariant system. A system with 2 degree of freedom is called as the bivariant system. If the number of degree of freedom is equal to the 0, that is F is equal to 0, the system is called as the invariant or the no variant or the non-variant system. So, here the univariant, bivariant or the zero variant system. Then let us consider some examples. So, first example is the ideal gas. So, what is the degree of freedom of the for the ideal gas? What is the value of the F for the ideal gas? So, ideal gas behavior is governed by the equation PV is equal to nRT. So, all of you know that this is the ideal gas equation, PV is equal to nRT. If the pressure and temperature are fixed, or if the pressure and temperature are specified, then the volume automatically get fixed. So, here for a given quantity, from this equation we can write V is equal to nRT by P. So, here hence pressure and temperature can have any value. The value of volume depends on them. That is, here in this case, when we consider the ideal gas, the volume of the ideal gas, it depends on the pressure and temperature. So, here in general, selecting any two variable automatically fixes the third factor. So, here when we select the temperature and pressure, volume is automatically fixed. So, here in case of the ideal gas, F is equal to 2. So, here when we consider the single gas, the single gas is the bivariant system. So, here if we have to define the system, a single gas or the ideal gas, here we have to specify the two variable such as the temperature and pressure. So, here F is equal to 2. Then let us consider the next example, that is the mixture of the two gases. So, here consider the example of the mixture of the two gases. So, here chemically not reacting. To define such a system, one will have to mention the percentage of the gas, that is a composition, temperature and the pressure, and it gives the perfect idea about the gases phase. So, here when we consider the mixture of the two gases, so here to define the system, we have to mention the percentage of the gas or composition of the gas, temperature and pressure, then it gives the perfect idea about the gases phases. So, here when we consider the degree of freedom for the mixture of the two gases, so here degree of freedom is 3, or the system is the trivariant. So, degree of freedom is 3, that means here we have to specify the composition, temperature and the pressure. So, here for the mixture of two gases, F is equal to 3. Then the next example, vaporization of the water. So, here let us consider this equilibrium, water and water vapor. So, here both the phases are the same chemicals, that is a H2O. So, here the composition term is dropout. So, here in case of the water as well as the water vapor, here both the phases are the same chemicals. So, the composition term is dropout. The system water in equilibrium with the water vapor has two variable. Which are the two variable? The two variables are the temperature and the pressure. At a definite temperature, the vapor pressure of the water can have only one fixed value. So, friends, all of you know that at a definite temperature, the vapor pressure of the water can have only one fixed value. Thus, if the variable temperature or pressure is specified, either temperature or the pressure is specified, the other is fixed automatically. Hence, when we consider the vaporization of the water, the degree of freedom F is equal to 1. So, here to define the system completely, vaporization of the water, either we have to specify the temperature or the pressure. So, here the degree of freedom F is equal to 1. This is the third example. Then the next example, ice, water and water vapor system. It is the three-phase system. So, here the ice, it is in the solid state, water it is in the liquid state, and vapor it is in the gaseous state. So, here it is a three-phase system. So, ice is equilibrium with the water and water is equilibrium with the water vapor. The three phases can coexist in equilibrium only at one particular pressure and under one particular temperature, that is the freezing point. So, here the ice, water and water vapor, these are the three phases, and here there is an equilibrium between the three phases at fixed pressure and fixed temperature. So, here any change of this factor, that is the temperature and pressure, will ultimately disturb the equilibrium, leading to the disappearance of the one phase. As we change the temperature or as we change the pressure, here what happen? It disturbs the equilibrium, leading to the disappearing of the one phase. That means the one phase will be disappear. It means we have to not specify the temperature as well as the pressure. So, here when the water, ice and water vapors, if they are equilibrium with each other, so here at equilibrium there is a fixed value of the temperature and pressure. So, it is not necessary to specify the temperature and pressure. So, here when we consider such a system, so here such a system has no degree of freedom, or it is known as the non-variant or the zero variant system. So, here if the three phases are in equilibrium, such as the ice, water and water vapor, here F is equal to 0. So, these are the some example just to understand the concept of the degree of freedom. So, friends, in this lecture we have discussed some basic terms or basic concepts of the phase rule, such as the phase rule, then the definition of the system, definition of phase, component and degree of freedom. Thank you.